Today's topic is clustering. My name is Johan Hagelbeck and I'm Senior Lecturer in Computer Science at Linnaeus University. Recommendation systems, that we talked before in the previous lecture, is one way of, for example, finding users similar to yourself. We will now look into a related method called data clustering. It is used for discovering and visualizing groups of items, people, blog entries, etc. that are closely related. We will take a look at two different algorithms, the hierarchical and the k-means clustering. First, we need a dataset to work with, and the dataset we will use in this lecture consists of 120 blocks, and this is the same dataset as you will use in the clustering assignment. The data for each blog is the number of times a particular word appears in the blog feed. There are in total 706 pre-selected words. The data is in a tab-separated text file, and a small subset of the data looks like this. So we have a dataset, and we have some blogs as rows, the Gotamist, GigaOM, and Quick Online Tips, and we have the unique words and the occurrences, the frequencies for all these words in the blogs. So kids appears 3 times in Gotamist, 0 times in GigaOM, and 2 times in Quick Online Tips. The word Yahoo appears 0 times on Gotamist, 2 times on GigaOM, and 22 times on Quick Online Tips. And the basic idea is that if we can cluster blogs based on word frequencies, we might find groups of similar blogs. It can be useful when searching, cataloging, and discovering online blogs. And the dataset can be downloaded at the course web page. And of course, it's also possible to generate a new dataset using a blog feed parser tool or a dataset about some other topic than just blogs. A larger part of the dataset looks like this. So we have the rows, the blogs, and the unique words as columns: China, kids, music, you, want, wrong, service, tech, and so on, and the occurrences of these words. The first algorithm we're going to talk about is hierarchical clustering. In hierarchical clustering, a tree hierarchy of groups are constructed by continuously merging the two most similar groups. So each group starts as a single block, and in each iteration the distances to all other groups are calculated and the two closest ones are merged to form a new group. And this is repeated until we only have one large group. So we can start like this. We have A, B, C, D, and E, the groups. That's our blogs, and each blog are in one separate group, and we can visualize them in some space here. So in the first iteration, we could find that A and B are the closest one. So we merge the A and B groups to form an A plus B group, and we still have C, D, and E groups. So now we have 4 groups instead of 5. In the next iteration, we find that the C group are closest to the A plus B group. So we form a new group that consists of A, B, and C. And we still have the D and E groups. In the next iteration, we find that the D and E are the closest ones, so we merge these two. So now we have 2 groups, A plus B plus C and D plus E. And in the final step, we merge everything together because we only have 2 groups left, so we merge them into one. And then we have the root group in our tree hierarchy. And we can display the hierarchy in a graph called a dendrogram, which displays the nodes arranged into a hierarchy. So we start with all the 5 blogs here, and each blog is in one group each. And the first thing we did was merge A and B. Then we merged the A plus B group with C, and then we merged the D plus E group, and finally we merged the D plus E group with the A plus B plus C group to find the root group. Central to this algorithm is a measure of how close 2 blocks are, and in the previous lecture we defined 2 similarity measures, Euclidean and Pearson. In the dataset we use here, some blogs contain more words than other blogs since they have more or longer blog entries. And Euclidean is not a very good measure in this case, so we will therefore focus on Pearson. The more similar 2 blocks are, the smaller the distance value between the blocks. So if 2 blocks match perfectly, Pearson returns 1.0. If they don't match at all, Pearson returns -1.0. So the Pearson value must therefore be inverted. So the Pearson distance is calculated as follows. So I want to calculate the Pearson distance between the two blocks A and B. We start by init variables, sum A, sum B, sum A squared, sum B squared, and P sum. And the number of words is 706, we know that, so we can hard code it. And then we iterate over all words. First, we get the word counts for the current word on index I for block A and block B. We increase the sum A and sum B with the word counts, and we increase sum A squared and sum B squared with the word counts raised to the power 2. And when we increase P sum by calculating the word count for A multiplied by word count for P. And then we calculate the Pearson, the numerator as P sum minus sum A multiplied by sum B divided by n. The denominator is the square root of sum A squared minus sum A to the power of 2 divided by n, multiplied by sum B squared minus sum B raised to the power of 2 divided by n. And when we return the inverted Pearson score, so 1 minus numerator divided by denominator. If we implement it, we must have some form of tree data structure. So it's recommended to model all these clusters or groups as a tree. And each node, which we call a cluster here, in the tree contains either a block, which could be a leaf node, which is a leaf node, or two branches to other nodes. We will also say the distance measure between the two branches, or 0 if the node is a leaf node with a block entry, and a reference to the parent node. So the data structure will look like this. We have a reference to the left cluster, reference to right cluster. We have a block entry if we are on a leaf node, otherwise it's null. And we have the distance, which is 0 if it's a leaf node, the distance between the left and right cluster. So we can visualize it like this. We have a blocks A, B, C, D, and E, and each are in one cluster each, and they have reference to the parent. And the parent in turn has reference to the left cluster and the right cluster. That's the A and B cluster. The A and B are merged together with C, so we have C, A, B, C here. And it has a reference to the left cluster, which is A plus B, and the right cluster, which is the C. And all the clusters have reference to the parent node as well. And we continue like that, merged D and E, and then we finally merged the two groups to form the root group. Merging two clusters A and B can be a bit tricky. Now we have to do the following steps. Create a new cluster called P, set P dot left to A, P dot right to B, create a new block BP for cluster P, fill the block by averaging the word counts for each word from the blocks in A and B, set A dot parent to P, set B dot parent to P, and set the distance score to P. In code it looks like this, so we have to do a merge between cluster A and cluster B, and that should return a new cluster. And we also need the distance between cluster A and B, distance score. 706 words, we create a new cluster P, we fill P with some data. P dot left is A dot parent is P dot right is B, and B dot parent is P. And then we merge the block data by averaging the word counts for each word. So we iterate over each word, and we get the word count for each word in cluster A and cluster B, and then we calculate the average word count, and then we set the new word count to the new block. And when we set the block to the new cluster and set the distance, and then we return the new cluster. So we need some form of hierarchy generation algorithm. So we start by generating one cluster for each block, and then iteratively merge to two clusters one at a time until only one cluster remains. So iteration looks like this. Find the two closest node. So we find the distance sets to max value as starter, and we have cluster A and cluster B. We iterate over all clusters into for loops, and then we check the distance between them, and then we see if the distance is less than the closest distance and the blocks are not the same. Then we have a new set of closest nodes found, so we set the new closest distance, we set the new closest cluster A and B. And when we have found the two closest ones, we merge them with a merge algorithm. Then we add the new cluster to the group of clusters, and then we remove the old clusters A and B. So we only have the merge cluster in the list. And if we display the result, it could look something like this. So here we have some blogs that are related to each other, Google Blogoscope, Google Operating System, Search Engine Roundtable, official Google blog, Read Write Web, Search Engine Watch blog. So these are blogs that looks like they are talking about related things at least. And here we have some gamer blogs, then official Apple weblog, Joystick, Cooler Heads Prevail, Download Squad, etc. We have to take some performance issues in consideration. Calculating the distance score between two blocks of 706 words is rather time consuming, and the algorithm iterates several times, 98 in our example dataset. In total, 161,700 similarity measures are calculated, so it might take a while to generate and display the tree. So think about if you can find any performance improvements when you implement it. The second algorithm we're going to talk about is k-means clustering. Hierarchical clustering has some drawbacks. Data is not broken down into distinct groups without additional computation. We just merge two groups at a time, and the algorithm is very slow. An alternative is to use k-means clustering. It is quite different from hierarchical clustering because we tell the algorithm in advance how many clusters we want. The algorithm will then determine the size of each cluster based on the data and will move the blocks to one of these predefined number of clusters. Central to this algorithm is centroids. The centroid is the point in n-dimensional space that represents the center of a cluster. Each centroid is placed at a random point at the beginning of the algorithm. This means that for the blog data example we have 706 words, so each centroid must then have 706 randomly generated counts ranging from min to max count for that specific word. For example, the word China occurs between 0 and 11 times in all blogs, so it never goes over 11 times. So the random count for this word must be between 0 and 11. So the algorithm works as follows. Decide how many clusters that are needed, called K. Randomly place K centroids. Assign every block to the closest centroid. After all blocks have been assigned, each centroid is moved to the average location of all blocks assigned to a cluster. So it moves to the center of a cluster. And then we repeat for I iterations. And for each iteration, we clear the assignments, assign every block to the closest centroid, and move centroid to the average of the clusters. So it could look like this. We randomly place two centroids, and we have the A, B, C, D, and E blocks here. And the blue circles are our centroids. And we assign the blocks to the closest centroid. So A and B are assigned to this centroid, and C, D, and E are assigned to this centroid. The next step is to move the centroids to the center of a cluster, so something like this. This is where we place one cluster centroid, and this is where we place the other cluster centroid. So we move them to the center of all blocks assigned. So here we have A and B assigned, and here we have C, D, and E assigned. The next step is to reassign the blocks to the closest centroids. So now we clear the assignment, and we get new assignments, and we see that A and B are of course closest to the centroid, or the top centroid, but now C are instead closest to the top centroid, and D and E are closest to the bottom centroid. And then we move the centroids to the center of a cluster. So here we moved this centroid to the center of A, B, and C, and here we moved this centroid to the center of D and E. And then we continue until we reach a stable solution where no new assignments are made. So algorithm looks something like this. We have 706 words, so we can hard code it because we know that. And we generate k random centroids and place them in a list. So we create a list and the list we shall add k centroids to the list. So we have a for loop where we create a new centroid, and when we calculate a random word count for each word, and that word count is a random integer value between the mean and the max counts for these specific words in all the blocks. And then we have iteration loop that goes from starts and goes to a predefined max iterations. First we clear all assignments for all centroids, and when we assign each block to the closest centroid. So we iterate over all blocks, tries to find the closest distance, and we set it to max value for a starter. The best centroid is we need to keep track of. We iterate over all centroids, calculate the distance using Pearson between the centroid and each block. And if we calculate the distance is less than the best distance, we have a new best centroid. And after we have checked all the centroids, we assign the block to the best centroid. And then we have to recalculate the center for each centroid. So we iterate over all centroids, and for all centroids we need to find the average count for all the words. So we iterate over all the words from 0 to n, calculate an average value, so we need to go over all blog assignments, increase the average variable with the word counts, and then divide the average value by the number of assignments to get the average value. And then we set the new word count to a new centroid with as the average value. And then it's the end of iteration loop. All is done. So when is it finished? The algorithm must stop the iteration at some point. To do this, you can define a maximum number of iterations, for example 20, and hopefully it is stable after 20 iterations. Or always stop if a previous assignment is identical to the new assignment, so no new assignments, all blocks are assigned to the same centroids. We can visualize clustering in my web-based clustering demonstrator tool here. So it looks like this. We select a dataset, we can select this dataset, and we select an algorithm, k-means here of course. We can also set some parameters, and then we run the visualization, and we see we have 4 fairly distinct groups here. And if we run k-means, you see that the centroids, the red squares, move, and after a while, after 14 iterations, they are stable, and we have these 4 fairly good assignments. So if we run it again, we see that they are randomly placed and they are moved to the center of the assignments, and after a while we get a stable solution where all the groups are quite good separated. So we can try another data set here, and we see that we quite fast, after only 6 iterations, reached a stable solution. So which one should you use, hierarchical or k-means? K-means requires very few iterations compared to hierarchical and is significantly faster. K-means is initialized with randomly placed centroids, therefore the result can differ between executions. Hierarchical is always consistent, and in k-means you also must predefine the number of clusters you want. So if we run k-means on our blog dataset, we have 2 different runs. You see that the results differ a bit, but some blogs that are very close to each other usually end up in the same cluster, and that we can use to verify that our implementation works. So we have a Google operating system, search blog, search engine watch blog, search engine roundtable in this cluster, and they end up in cluster 2 in the other run as well, Google operating system, search blog, search engine watch blog, official Google blog, etc. We also see that the gaming blog, Maverick, joystick, download code, and gadget or tech blogs is in the same clusters. So that's all I had to say about clustering. Thanks for listening.